Hi ET250 students. I hope you're enjoying the break without class and staying healthy with the fresh indoor air. I just wanted to go over another problem that was in office hours that maybe not everyone got to see. So hopefully this will help with understanding from the previous homework. Okay, so this is problem 2.108. And what we have is a Wheatstone bridge. We have a voltage source, R1, R2, R3, and RX, and a voltmeter or detector. And the question asks, can you please find the VT and RT, or essentially the Thevenin voltage and resistance, as seen by the voltmeter? Okay, and so I put two terminals A and B, so we're going to essentially cut out the voltmeter and treat it like a normal Thevenin problem, and we're going to do everything symbolically. Now, once we get that Thevenin voltage and resistance, or that Thevenin equivalent, what we're going to ask, or what the question asks, is what is the value of VT when the bridge is balanced? And if we recall from the lecture, the balanced situation is when VAB, or the voltage across this voltmeter, is 0. And we also proved to ourselves that the resistors must have this relationship, Rx equals R2 over R1 R3. Okay, so let's tackle the first problem for and then let's do the next one. So if we look at this, well, the nice thing is that they're all independent sources. Well, we only have one source, so we can literally just find the equivalent resistance between A and B with this shorted. So let's just redraw the problem. So we have short, and we have A and B. This is R1 and R2. And then we have R3 and Rx. Okay, and then we have the short right here. Okay, and we want to find, like I said, the equivalent resistance between RAB, because R equivalent equals RT for our Thevenin resistance. And let's see if we can find any easy situations to use the parallel or series laws. And if we look at these two, it's tempting to say that these two are in series, right? And they are. But the problem is, if we were to combine R1 and R3 in series, we would lose RA. Likewise, R2 and RX are technically in series, but we would lose point B. So we don't want to do that. Now, if we look closely, this is a little tricky to see, R1 and R3 are in fact in parallel due to the short, and we can do our test. If we look at these two connections, they touch, good. And if we look at these two connections, they also touch, so yes, these two are in parallel. Likewise, R2 and RX are also in parallel, and do a test again. These touch, good, and then these 2 points touch. So if I were to redraw this, let's see, if I had point A and point B, I could draw R1 and R3, okay, and this point here is this short here, and that connects over to R2 and RX. R2 and RX, and hopefully this becomes a lot more clear to see that these two are in parallel and these two are also in parallel. And then once we find these two equivalent resistances, they are in series. So R equivalent 1 and R equivalent 2 can be found by this, R2 parallel RX, and R equivalent 1 is R1 in parallel with R3, okay? And then the total REQ is R equivalent 1 plus R equivalent 2, because they are in series. So to write out that full formula, R equivalent equals RT is equal to R equivalent 1, which is just this parallel combination, R1, R3 over R1 plus R3, plus then this R equivalent 2, which is just R2 RX over R2 plus RX, and the units, of course, would be in ohms. So this is our Thevenin resistance from the perspective of AB, or this voltmeter. Okay, let's keep moving on. Let's find the VT. Okay, so what's the VOT? Well, we know the VT is the VOC. Okay, so now let's redraw this with the voltage source still in play, and we will look for the VOC, which is the VT. Okay, let me redraw this again. Okay, this is R1, R2, R3 Rx. Okay, and this is still point A, this is still point B, and we have plus or minus VOC, right? Okay, so we want to get this open circuit voltage. How do we do that? Well, there's many ways, but let's define a ground here. Maybe we can use some nodal analysis. So if we notice, we have VOC, which is the same as VAB, right? First letter is the positive, second letter is the negative. Good, it's the same. If we want to define VA, which is the node here, and the node VB, we could use a voltage divider scheme. And once we find VA and VB, we could use a KVL and get VAB. So if we write that down, KVL, VAB equals VA minus VB. And you could do it slower. You could say minus VA plus VAB plus VB equals 0. And you can quickly see that this results in that, right? Okay, so we have this. So the problem goes from, if we want VOC, which is VAB, which is VT, we can solve for VA and VB, and then we're done. So how do we get VA and how do we get VB? Well, we have a voltage source and two resistors in series. Screams voltage divider. So VA is equal to the source voltage times the voltage that we're looking at, or the resistor for the voltage we're looking at, R3 in this case, over the sum. Okay, and then VB is the same pattern. VB, voltage divider again, equals VS times RX over R2 plus RX. R2 plus RX. Good. So now we just say, okay, VT is equal to just the subtraction of these two, which is VA R3 over R1 plus R3 minus VS times RX over R2 plus RX. And this will be units of volts. And this is our Thevenin voltage for the equivalent Thevenin circuit as seen by A and B, or this voltmeter. All right. So what does that mean? That means if we had this circuit between A and B, this entire thing could be replaced by this simple circuit as long as VT was this and as long as RT was this guy over here. Okay, so then the next question asks, what is the value of VT when the bridge is balanced? Well, that should be pretty straightforward. So VAB is 0. That's our balance condition. Well, if that's the case, VT must be 0. Now in office hours, I apologize, I was super tired and I was just having a brain fart. But if this voltage is 0, you can quickly see that this is going to be 0, right? No current, we're all good. Now, let's just try to go one step further. And we know this condition is true if the bridge is balanced. If we take this and plug it into here, perhaps we can get a cancellation, right? And so let's just try it. So if balanced, we know that Rx equals R2 over R1, R3. And let's just see if VT is equal to 0 if that's true. Okay, so we're going to take this and plug in for everywhere we see Rx, we're going to plug in this relationship. So let me get a new piece of paper out. Okay, so we're going to take VT is equal to VS R3 over R1 plus R3 minus VS. And now we're going to plug in this relationship for Rx. So it's R2 R3 over R1 divided by R2 plus R2 R3 over R1. All I did was take that Rx and replace it with that known relationship for balanced. Okay. Now it's just a matter of algebraic crunching. So let's see what we get. So we get VS, I can pull a VS from both sides, times R3 over R1 plus R3. And let's see if we can, before we move on from this step to this step, if we can make some cancellation. Well, if I multiply the top and bottom by R1, that changes nothing because it's like multiplying it by 1. And this cancels, but I have an R1 left over here. So I have R2, R3 over R1, R2 plus R2, 2R3. Okay, if I look at this and I see, is there any more that I can cancel? Oh, sure enough, R2's cancel. This is good. So now I have a VS times R3 over R1 plus R3 minus R3 over R1 plus R3. Oh, these are the same terms, so this whole thing cancels, this whole thing equals 0. And so what we just showed ourselves is that VT equals 0 when the bridge is balanced. And how did we confirm that? Well, we took the condition for the resistor when we know it's balanced, plugged it into an expression for VT, and found that, yes, sure enough, it is 0. Okay, well, I hope this helps your understanding for problem 2.108. I apologize in office hours if I was a little out of it, but yeah, I really hope this helps, and thank you for listening. Okay, bye.